differentiability. So when you're asked to confirm whether or not a function is differentiable, like the really elementary idea that we're looking for is a derivative can be calculated, can be found, which basically means it exists. Okay, so we can say a function's differentiable at a point, or it's differentiable across some interval if we can find a derivative for it. So we can say a function is differentiable on a to b for any a is less than or equal to x is less than or equal to b, which I should have written, if it has a derivative and the limits. So now we're going to test limits at the endpoints of that interval. So we're going to say the limit, and we're taking the derivative. Okay, so we want to see if the derivative exists at the endpoints. So the derivative will be found by doing f of minus f of, and I'm going to plug in a second, but I want to leave that blank for now. So we're going to check the left endpoint, which is at point A. So if we're checking the left endpoint, we want to see the distance between the point we're currently at and the left endpoint. The distance between those approaches 0 as we go from the right, okay, because we're approaching the left endpoint. Now we're going to have a plus h in here. Now, if I'm approaching the left endpoint, we want to evaluate that limit definition of the derivative at the left endpoint. So we're going to see a. Okay. If we're approaching the right endpoint, we want to evaluate the limit as h approaches 0 from the left, because we're approaching the right, f of plus h minus f whole over h. And again, if we're approaching the right endpoint, in this case, we'll evaluate our limit definition of the derivative at point B. These two things here, these are called one-sided derivatives. And for this thing to be differentiable at the endpoints, these two derivatives need to exist at A and B. Now, if we're looking at differentiability, we can start with, well, where do we fail to have differentiability? That can often help identify if we do have differentiability. So, a derivative fails to exist when? So case number 1, there's a corner. And we don't want to just say there's a corner. We want to put some rigor to our reasoning. And at a corner, again, visually, we could see something like that or that on our graph. At that corner piece, a derivative will fail to exist. Now, reasoning, we're going to say the limit. So we'll say A is where the corner exists. So let's add that in. So at x equals A, there is a corner. Your justification as to why it's not differentiable, you would say the limit. Again, differentiability is all about the derivative itself. So we want to take the limit of the derivative as we approach the corner from the left, and the limit of the derivative as we approach from the right will not be the same. This is our justification for why a corner, we don't have differentiability. And if you just look at a corner, you can see once you're at that corner, if the derivative is found through the slope of the tangent line, the question usually comes in, like the way I like to think about it is like, well, where do I draw this tangent line on this corner? Do I draw it like that? Do I draw it like that? Okay, do I draw it straight across? Like, because it's not obvious, that's the reason, that's why, the way I like to think about why at a corner there's no derivative to be found, but the actual justification, we're going to say the limit as we approach A from the left and right of our derivative values aren't equal as we go towards that corner. And again, you can see that in case the corner is going to be formed by two linear pieces, the slope on one end and comparing it with the slope on the other, they don't match. The second case will be a cusp. The cusp will look something like this. And our justification, again, it's not good enough just to say, oh, there's a cusp there. You have to give a limit reason. There is a cusp. And your reasoning is, as you approach the cusp, so the derivative itself, as you approach the cusp from the left equals plus or minus infinity, or the limit as you approach the cusp from the right equals plus or minus infinity. Okay? And so essentially these are approaching a complete vertical line, and because of that, vertical lines we know have undefined slopes. So if we can't define the slope, we can't define a derivative. So that's your reasoning for the cusp. Option 3 will be a vertical tangent. So that will happen in certain functions where at a point that we approach the tangent line, again, I'll try to draw that actually a little bit steeper to better illustrate the point. So the graph is still a function, doesn't fail that vertical line test. But as we approach that point right there in the middle, we're gonna approach a vertical tangent line, and that's going to be a failure for a differentiability test. So at x equals a, there is a vertical tangent. If we've identified that, then our reasoning is going to be the limit of f prime of x as x approaches a from the left is equal to plus or minus infinity, or the limit of f prime of x as x approaches a from the right equals plus or minus infinity. So again, it depends on the picture, but you can see as I draw in tangent lines, there's one, and then as we're approaching that, they start to get more and more vertical. And again, if the tangent line is vertical, a slope can't be defined, and so we do not have a derivative there. Then the last possibility is a discontinuity. If the function's not continuous at a point, well, there's no derivative to be found, right? So if you identify discontinuity, the function is not differentiable, okay? And we already have a way to define continuity, and that would be your justification. So, checking for differentiability. One, verify continuity. That's step one. The function is not continuous, we don't even have to move on. So verifying continuity, we're going to use our definition of continuity. We want to confirm that the limit of the function as we approach that point where we're checking differentiability is equal to the function output at that point. 2, check limits of derivatives. And what we're going to do, this is the differentiability part, we're going to say the limit of f prime of x as we approach this point from the left needs to equal the limit of the derivative as we approach from the right. Okay, this is your test for differentiability, so know this. Okay, if you want to star this, highlight this, we need a way to check for differentiability. Step 1, check continuity. That's really important. People often forget that. And then check the limits at the derivatives. or the limits of the derivatives at that point. So I'm just going to run through a couple quick examples so you can see how this works, and that will conclude the video. So example, we have a piecewise function, x squared when x is less than 0, and it's 2x when x is greater than or equal to 0. So we want to see, the question would be differentiable at x equals 0. So let's check that. First thing, we check continuity. So continuity, so we're going to say the limit of f of x as x approaches 0 from the left is equal to 0 squared, which is equal to 0. The limit of f of x as x approaches 0 from the right is equal to 2 times 0, which is 0. F of 0, so again, don't forget to check the output, is equal to 2 times 0, which is equal to 0. Therefore, the limit of f of x as x approaches 0 is equal to f of 0. So therefore, the function f of x is continuous. So step 1, complete. Now we have to check differentiability. So derivative check. We want to see what is the limit of the derivative as we approach 0 from the left. Well, we have to find the derivative of each piece. So the derivative of x squared, if you run through your limit definition of a derivative, is going to be 2x. And for a linear function, we don't even have to run through the limit definition. I can see that the slope of my linear function, which represents the derivative, is going to be 2. So we're going to say the limit of the derivative as we approach from the left, we'll be looking at that top function. So that is going to be two times 0, because we're plugging into the derivative now. So we're plugging into 2x, which is 0. And we're doing limit of f prime of x as x approaches 0 from the right is equal to just 2. So therefore, the limit of f prime of x as x approaches 0 from the left is not equal the limit of f prime of x as x approaches 0 from the right. So f of x is not differentiable at x equals 0. We can do one more. Last example, is this absolute value function differentiable at 3? So we know absolute value functions, all that's happened here is like a basic transformation. So we know it's still continuous, so the question would be checking differentiability. Differentiability of absolute value using the limit definition can be tricky, so our understanding of the graph can help. And what we're going to find is that this minus 3 here, hopefully you recognize, we have a translation right 3. And we know with absolute value, add 0, it originally has a corner. So if I slide it right 3, now the corner is at 3, which is where I'm testing differentiability. And we said at corners, functions are not differentiable. But our answer should not be, it is not differentiable because we have a corner. Rather, it should be f of x is not differentiable at x equals 3. We could say there's a corner, but we want to add on the limit part. And therefore, at corners, the limit of f prime of x as x approaches 3 from the left does not equal the limit of f prime of x as x approaches 3 from the right. Now, before I end the video, I want to highlight one important thing with notation. Again, when we're checking the derivative differentiability piece, so the limits of the derivative, make sure your limit notation is of a derivative, f prime. Don't put f of x. We're testing the derivatives of the functions, so make sure you put in a derivative notation for your limit on that piece. And make sure we're sticking with just f of x when we're checking continuity. So make sure we see the difference. Like here with continuity, I'm just dealing with f of x. When we're checking derivative limits, we're looking at the actual f prime. So I want to add one more thing with checking for differentiability, because we have to check continuity as well. This is really important, because differentiability is necessary. It's necessary for the function to be continuous. If we are actually told a function is differentiable, then that implies that the function is also continuous. So let's start that really important AP concept. If a function is differentiable, then the function is continuous. So what this is saying is differentiability implies continuity. So section that off somewhere. Differentiability implies continuity. If we're told the function's differentiable, we know it is continuous. Very important to understand. And that is the conclusion to differentiability.